Hi, I'm Tom Gleason, an associate professor and president's chair at University of Victoria. Here in this talk, I want to answer two questions that have been pressing on my mind. Why is groundwater sustainability important? And should the pandemic change what I do as a sustainability scientist? To try to for us to think broadly about these two questions, I want to start with two quotes. The first quote is from Gandhi, and it is, "The earth provides enough for every human's needs, but not every human's greed." The second quote was actually scrawled on my neighbor's garage door during the pandemic. And I found it very inspiring as I walked around banging my pots with my son and my family. And this image really just inspires me well. And it is, "As the world separates us, we come together." And so I want you to keep those two quotes in mind as we move through this talk about groundwater. And so what is groundwater? It is often forgotten, but it's always beneath the ground. We've all had the lived experience, you can dig back in your memory at some point, of digging a hole at the beach. It was first dry, and then there was a little bit of moisture, and eventually you hit water. And what you hit was groundwater. It's beneath our feet almost everywhere in the world, and it's the water that's caught in rocks or stored in rocks, and the cracks in rocks or in sand and gravel. And that's the water that we're going to be talking about mostly today. Why is it important? Well, I first want you to actually pause your video for a minute and try to answer this question. What percentage of the fresh, unfrozen water on Earth is groundwater? Is it 1%, 5%, 20%, 50%, or 99%? So I'll give you a moment to pause your video. And for those of you who guessed the really big one, 99% is the correct answer. The vast majority, basically almost all of the fresh, unfrozen water on planet Earth is groundwater. So it's a hugely important resource for humans, ecosystems, and food production. The second kind of amazing fact about groundwater is that it's very old. So the median response time, so response time is how long groundwater takes to respond to a change, is about 1,600 years old, so 1,600. So if we put that in human terms, that's roughly when the Roman Empire was falling. And that's why I have this image in the back of the Colosseum falling to pieces. So we think that you should also think in the back of your mind that groundwater is very old and it's a very large resource. Before we get into the talk, I want to talk a little bit about me and about my research group to give you more perspective of where I'm coming from. The first about me, where I started, is as an undergraduate here at the University of Victoria as a geologist interested in the Earth system. So I was banging on rocks and taking samples and making maps of rocks in northern British Columbia and in the Himalayas. And then I did my PhD. I switched gears a little bit to civil engineering to study groundwater. That's what the study of groundwater is called, hydrogeology. And in that, I really became passionate about water resources writ large, as you'll see through this presentation. And more recently, as a postdoc and then as a professor at McGill and now here at University of Victoria, I'm an engineer and geoscientist. I straddle those two divides and interact with a number of other disciplines as well. And most often I synthesize and model data, and that's what my research group does. So a little bit more about my research group. We really are always thinking of ourselves within the Earth system. So this is an image of the Earth system. The system has different components of the atmosphere, the biosphere, the geosphere where all the rocks are, and the hydrosphere. And most of our work is focused on the hydrosphere. That's kind of a jargony, technical word for the water cycle or the hydrologic cycle. And so the hydrologic cycle, this is an image that all of us would have seen at some point, I think, of water evaporating from the ocean, raining and precipitating on the land, and then some portion of that getting down into the subsurface, which is what we focus on. So most of my research group focuses on hydrogeology, that's the study of groundwater, across multiple disciplines of engineering and geoscience, but also geography and policy studies, and at multiple scales. And probably most importantly, we actually really care about humans as well. So we don't just study the Earth system in an abstract scientific way, but we always and inherently consider humans to be part of our research. And that's why our research group is called the Groundwater Science and Sustainability Research Group. And that's some of our research is what I'm going to be talking about here today. So the talk is organized into three sections. The first is 5 reasons to care. And those reasons are, as a quick summary to get you start to get thinking, is that groundwater connects various parts of the Earth system. Groundwater is a critical resource. Groundwater maintains ecosystems, which are impacted by pumping. Groundwater sustainability is threatened globally. And water policy often just forgets or is not aligned with groundwater hydrology. So in the middle part of the talk, I'm going to kind of bring together our kind of a current situation in the coronavirus pandemic and groundwater, and end with kind of combining these two topics as 5 ways to move forward. So the first reason to care is that groundwater connects various parts of the Earth system. I already highlighted that we think of groundwater in relation to the rest of the Earth system. We've studied, and I'm going to talk about the relationship between groundwater and climate in a little bit more detail. So I'm going to do a little bit of a deep dive on groundwater and climate in the next few slides. We've also explored the relationship between groundwater and oceans, how groundwater contributes a limited amount of water to the oceans, but that can be very important to the chemistry of the oceans. Groundwater in the subsurface on land is also important for the weathering of soils, like how we create soils, for how faults and earthquakes occur and where they occur, and for mineral and petroleum resources. So those are all different aspects that groundwater touches in the Earth system. So now I'm going to take that deep dive into groundwater and climate. And to do that, I actually want to take you to one of my favorite places in the world. This is a small little village where I did field research in Nepal, to start to introduce where and how groundwater can be connected to climate. So this is a small village in what you can see is quite an arid region. And the black line I've drawn here is what I would imagine if I was looking at this landscape. So the black line is the water table. And the water table is is a surface where below it is fully saturated in groundwater. So in the village area, it's very green. That's where water tables are very shallow. They're very near the surface, and that groundwater is supporting those plants to grow and be green. In the mountainside, where it's very dry and arid, the water tables would be very deep below the surface, and there'd be very little connection between the water table and the land surface, and there'd be very little evaporation. We can get a little bit more technical about that and talk about 2 different types of groundwater climate interactions. And I've labeled these as 2 different colors of water tables here. The blue is what we call bidirectional groundwater climate interactions. These are these shallow water tables where precipitation can go down and evaporation and transpiration through plants can go up. So there's a 2-way bidirectional movement of water across and between groundwater and climate. In the red areas, we have these deeper water tables, and the groundwater precipitation can go down, but really the evaporation doesn't go up. So we have this unidirectional connection between groundwater and climate. So I'm going to use this terminology in the next few slides. Unfortunately, as a groundwater hydrologist, climate models have largely ignored groundwater. So they don't include the lateral flow of groundwater, so how groundwater flows from one place to another. And so the question here in this kind of science part of this talk is groundwater actually connected to other Earth systems like climate? And I'm going to use this terminology of these connections to walk through this. So as I highlighted before, you can basically think of these 2 different water tables as more connected and less connected. And since this seemed a little abstract to me, I wanted to bring this into something we definitely know, which are social connections. So on the left-hand side is a social connection. And that social is I would say, a strong social connection between an older man and a younger girl who stopped for a minute on her bike and is conversing with this older man somehow. And on the right is a kind of a less connected situation. I wonder why it's so slow. Maybe the lines are tangled again. This is an older woman who's struggling somehow to connect through her computer, probably with somebody else, either through social media or some of this. So I want to use these 2 images to explore what connection means in hydrology and in our social system. So I'm going to ask you again in a minute to pause as a warning, but I want you to first think about and remember a time when you felt a social connection between 2 people of quite different ages. So an older person in your life if you're a younger person, or a younger person in your life if you're an older person. And I want you to think to yourself, how and why did that connection happen? And if you need a little bit of inspiration, you could look at these 2 different images and think, what is the difference in these 2 different images? So I'll give you a moment to pause and to remember and recall and think about what creates social connection. And for me, when I think about the social connection, I think, and I'm going to make this link with hydrologic connection, is that social connection, first of all, often happens at the same location. So we've all experienced that over the last couple of months, a challenge of maintaining social connection while we've been physically distant. And there's a lot of discourse around social distance versus physical distance, but we all know that close proximity is important to social connections. The same two people have to be at similar speeds. And so this little girl was biking around very rapidly, and then for a minute at least, she stopped to talk to this older man. And that's how that connection happened. Then maybe they had something special that connects them as well, like food or common history. Maybe they're in the same family or friend group or some common interests. The hydrologic connections are very similar. They need to be in the same location, and they need to have a similar speed or rate. We're going to come back to speed or rate that I've already hinted at with groundwater in a minute. And so what we've shown recently in a paper that just came out last year is that about half of the world has these bidirectional groundwater climate interactions. So these are the blue areas on the map. And so those are areas where there's this really good, strong two-way connection between groundwater and climate. And then the rest of the world, getting into the reds on this map, are these unidirectional, one-way relationship between groundwater and climate. The other thing we've shown in this work is that groundwater has this very long response time. And I want to go back to this older man and younger girl here. In this image, you can see there's a graph with a whole lot of different wobbles on it. So that's the climate signal. So climate is varying through seasons, through times of day, and you can think of it as a highly variable, highly wobbling graph. Whereas groundwater is a much more slow and smooth response. So you can really think of it as this difference between a young, active, changing, dynamic person versus a slow and more contemplative person. And so what we've shown is that groundwater has these very long response times. In all the blue areas of this world, the response times are up to 10,000 years old. And that has implications for groundwater resources, because what it means is that some of the groundwater resources in this world are still responding to climate changes over the last thousands or even tens of thousands of years. And it also is important because what we're doing to groundwater resources and where we're overusing groundwater resources and how climate is impacting groundwater resources could have very long-term, hundreds or thousands of years impacts into the future. And just as a reminder, came back to that image about that Rome is falling, and that's the median response time for groundwater that we've shown in this study. So in summary of about the connections between groundwater and climate, I would suggest that using this older man and younger girl is a good thing to keep in mind as a visual metaphor, that groundwater is connected to climate in many locations, but often at very different speeds. So with that, I'm going to move on to the second reason to care. And that this is most often what most people think about, that groundwater is a critical resource. In the background here, these are not alien crop circles. These are crop circles that were made by center pivot irrigation by groundwater that's tens of thousands of years old. So this is very old groundwater being used to irrigate crops and grow food, and is very important for beef production in the Midwest of the United States. This is in Kansas specifically. And so groundwater is very important for agriculture. Over 40% of irrigated agriculture is directly from groundwater. And groundwater is also very important for daily drinking. And so over a third of Canadians drink groundwater every single day, as I may right now. And over 2 billion people around the world, or almost a third of the global population, drink groundwater every day. Groundwater also maintains ecosystems. So this is an image of a salmon swimming in a stream in British Columbia. And groundwater is often cool and oxygen rich, and so that's important for maintaining salmon habitats in many rivers. And I've done a series of projects with a local company, Foundry Spatial, as well as BC Ministry of Environment and Climate Change and an NGO, the Nature Conservancy, to explore how groundwater pumping can impact streams. And this has been work done by two postdocs in my group, Sam Zipper and Kian Lee. And what we've shown is that stream flow depletion, what we call it, is very important. So when we pump a well, there's a little cross section, and the well is in the middle. The first thing that we do as we pump a well is the groundwater levels come down. That's called groundwater depletion, as groundwater permanently go down, and that's the red triangle in the middle. But the other thing, and the more important thing ecologically that happens, is that stream flow depletes. So we actually take water from our streams when we pump groundwater. And the problem with that in some ways is that it happens even more through time. So on this graph here is the time since the start of pumping on the horizontal axis, and the vertical axis is the source of pumped groundwater. And what we see is that through time, the importance of groundwater depletion goes down and the importance of stream flow depletion goes up. So as we pump for longer times, we're pumping from the river. We've known this for a while, and quite recently, a number of people have started to really care about this. The fish have always cared, but they don't have a very strong voice and don't speak English very well. What we have to do is we've now enacted legislation on their behalf. And that's partly for what the BC Water Sustainability Act is about. It's very exciting legislation that was passed and came into force in 2016 that for the first time links groundwater pumping with environmental flows. So these are the flows that are needed in rivers to protect the environment for BC for the first time. This is an opportunity as we continue to invest and develop tools in BC being world leading in water resource management. And that is also important. The last part of this slide here is for people. This is an image of a recreational reservoir that's been impacted by stream flow depletion. So our research has been trying to answer and develop tools to answer this question: how can managers quantify this stream flow depletion with limited time, budget, and resources? And I unfortunately don't have time in this talk to get into the details of this research, but I'm happy to provide details another time and in links below this talk. The fourth reason to care about groundwater sustainability is that it's threatened globally. This is kind of a strange map I made about 10 years ago where I made the rates of groundwater depletion. So that's how much we're losing and unsustainably using groundwater into topography. So the mountains of the world here that we see popping up are where we're unsustainably using groundwater. The biggest mountain is in Southeast Asia. So the biggest area of groundwater depletion is in northern India and Pakistan, but the other hotspots are in northern China, throughout the Middle East, North Africa, and in the American West. So this map highlights the water quantity problems and how we're depleting groundwater, but there's also significant groundwater quality problems, and we're contaminating groundwater in a number of areas. There's a limited understanding of this critical resource, especially at these scales. We often drill a single well, which is a very small area, and we have very few tools and they're just only emerging of how to address these large problems at these large scales. We also have very limited perspective on long-term policy and management. That's the last reason to care, in my opinion. That water policy often forgets or is not aligned with groundwater hydrology. So in this image, I'm showing the residence time of different parts of the water cycle. So we all know that plants have water in them. Water flows in and up of them. Any gardener will know that, and we need water. But that water stays in those plants for a very short amount of time, less than 1 week on average. Groundwater, on the other hand, has a very long residence time of 2 weeks up to 10,000 years. And that is very different from our typical government term of 4 to 5 years. So there is a massive and inherent mismatch between the perspectives and timescales of groundwater versus how we typically govern our societies. And with that, I'm going to move on to the second section of this talk, which is trying to make these connections between the pandemic that we're currently in and groundwater. So this question first came to my mind of how is the pandemic similar or different from the global groundwater crisis. The image here, the two images here are the COVID-19 virus itself and a dry stream driven by groundwater depletion. And we've written about this topic for the Circle of Blue. This was mainly contributed by a PhD student who's pictured here, Xander Huggins. And I'm going to summarize what we said in this recent piece in Circle of Blue, where we talked first about the commonalities between the coronavirus and the global groundwater crisis. And before I talk about the commonalities, I just want to really acknowledge that I fully understand and acknowledge that the pandemic is a very serious situation that has affected everybody's lives, our economy, and our health. And I don't in any way want to undermine that by comparing it to a different problem, but I just wanted to use what we've learned and what we're learning from the pandemic to suggest other methods to think about groundwater and the problems that I'm focused on in my research. So the first similarity between Corona-19 and the pandemic and groundwater is that it starts with local hotspots and has global impacts. So we all know the trajectory from Wuhan to other cities and places around the world, and now we have a globally distributed pandemic. The story is similar, but it's slightly more complicated with groundwater. Groundwater is used for irrigation in a specific place. That irrigation is used for specific products. So in the case of those crop circles, it was growing wheat, which was then going to beef, which then goes into hamburgers, which are then eaten in another place of the world. So we are moving this groundwater and the groundwater problems around the world in using what's called virtual water. This is the water embedded in products in the exact same way as things move around in the physical world. So our impacts of what we're doing around the world can be traced back to these local groundwater depletion hotspots. There are also, for both of these concerns, there were many warning calls. Bill Gates and many others gave a number of warning calls about a pandemic like we're in today. And myself and other colleagues have highlighted warning calls of groundwater sustainability and groundwater depletion. And there are, in both cases, regional examples to learn from. Currently, in British Columbia and lots of other jurisdictions, we're learning best practices around the pandemic from other places and other countries. And similarly, with groundwater sustainability, we can borrow lessons from other places. There are many differences between the pandemic and groundwater sustainability. The first is a rather wonky science and math nerd difference, and it's the difference in how the problem changes. We've heard a lot about flatten the curve. And so I'm just going to talk a little bit about graphs for a minute, because that's actually been one of the great things about the pandemic for me as a scientist, is we've been talking and seeing a lot of graphs. But we've heard a lot about how the pandemic is exponential. And what that means is that it changes very quickly. And that's very different than groundwater depletion. This is a graph of groundwater depletion. And that is very linear. And so some scientists think that one of the many reasons why our attention got caught very quickly on COVID-19 was this exponential change. Our minds are actually just not used to exponential change. We're more used to linear change and linear systems. And so the second major difference, which is apparent in these two graphs, is the recovery time. So we don't know when the full recovery from COVID-19 is going to happen, but most experts think it's on the order of months or years. Whereas groundwater, if we ever recover from the depletion that we're currently doing with groundwater, is over decades or centuries. So there are very different timescales of recovery and onsets of how the problem happened. So I want to use those insights to conclude with 5 ways of how to move forward. So the first is going back to this same graph of COVID deaths confirmed through time. And I want you can look, you've probably seen this graph or graphs like this, and we see them given out by our government and health officials, and were compared by different jurisdictions. And so I think we need to and can use the pandemic as an example. It's not a perfect example, I just highlighted major differences, but an example of the effort necessary to meet large global problems like climate change and like groundwater sustainability. This has been a sustained and highly impactful effort on our economy, on our society, and on our lives. And this is an example of the type of scope that we may need in some cases to meet some of these very vexing and important global problems. The second lesson that I think is important, and the second way to move forward, is elevating the good news stories. I think it's important to maintain our positivism, especially in these really challenging times. One of the efforts in my area of sustainability science is what's called seeds of the good Anthropocene. So we're planting seeds of these challenging times that we're in that grow into positive trajectories into the future. So I think that's an important way to move forward. The third is to manage groundwater over very long time scales. So as I highlighted earlier, groundwater moves very slowly through the earth, and we need to start to manage it over years or decades at a minimum, and so we can start to flow with groundwater in the way it flows. The fourth way forward that I think is important is that we need to insert groundwater into global sustainability frameworks. So I have two images here. The first image on the left is the planetary boundaries. This is a global biophysical framework for the perturbations of the Earth system that we're doing currently. Climate and climate change is just one of them. We're also perturbing and changing and impacting land systems, biodiversity, the ozone layer with aerosols. And groundwater has been largely ignored in this planetary boundary framework. Similarly, on the right is the United Nations Sustainable Development Goals, the SDGs that we often hear about. And groundwater is largely absent in these goals as well. It's inherently important in a number of them, such as growing food and for water and sanitation, but it's not explicitly given its due course. So I think it's important to enhance the perspective of groundwater in these important and well-used global sustainability frameworks. And finally, and more personally, I'm coming back to the question I started with. I think we should, and I, as a sustainability scientist, consider if the pandemic changes what I do as a sustainability scientist. And this conversation was really started by a piece in the Washington Post from March, which was about Isaac Newton, and the title was, "During a Pandemic, Isaac Newton had to work from home. He used his time wisely." He basically developed modern calculus and physics during a pandemic. And so some of my colleagues took this as extra pressure on us as academics. Others took it as inspiration, and I kind of landed somewhere in between. And so with a colleague of mine, Viviana Ray from Italy, who was locked in her apartment for 4 months, and while we were having these conversations, we were asking ourselves this question: what should we be doing? Should we meet this new problem and change our research? And what we've written about this in the blog that we contribute to, Water Underground, and I'll provide a link to that. And what we wrote about and argue is that there's really 3 options for us as sustainability scientists. The first is that we can kind of do status quo. We can just keep working, maybe run ourselves into the ground, have the same pressures and do the same work under these different conditions. Or we can, the second option is to go slow. So that is taking care of ourselves, managing our productivity and our stress and our life. And third is to innovate and experiment. And I've been doing, on different days and in different ways, I've been doing all 3 of these. It's not a linear thing that you just pick one and do only one. But that third one is really where I've been trying to focus my time, to think about new ideas, how groundwater relates to pandemic, for example, and how it could be important, or how groundwater is important for water sustainability and watersheds in BC. I'm trying to connect and work in my community. This video, even though it's not in person, is an example of that. I'm trying to imagine a better future and a better future for groundwater. Develop compassion in sustainability science, so that's part of my personal practice as well as with colleagues. and engage more broadly and deeply with partners and collaborators and community across BC and across the world. And one example of that is an effort that I led and has been very interesting and successful, which was the Global Groundwater Sustainability Call to Action. This has now been signed by over 1,300 practitioners and experts and scientists in over 100 different countries. And I'll provide a link to that. And I'll just conclude with a call to join the conversation. Check out the Groundwater Sustainability Statement, tweet a talk summary, check out the blog I mentioned, Water Underground, or check out our research webpage. And I just want to thank you very much for your attention, and I hope you answered those questions for yourself. And I look forward to hearing any interactions through comments or other ways. Thank you very much.